Now let's see the fourth substitution. Of course, we can take too many possibilities, but let's see one such possibility. Taking three methyl groups at adjacent positions, right? I've taken all the activators. Three substituents are already present. And now let us discuss what the fate of the fourth substituent is going to be. Consider chlorination of this particular substance. Now, if you check the positions, I mean, you have to check the ortho and para for every single, because all three are same, all three are activators, all three are ortho para. Let us check for this. Ortho blocked, ortho available, para available, right? Now, if you check for the second one, see for this, both the are blocked. One para is available. Now, if you consider, say this, one ortho is blocked, another ortho is available, and even a para. So anyway, looking at all these, we can come to a conclusion that all three available positions can of course be occupied because of one or the other methyl groups. Hope that is okay. Now, in the last one, yes. Now check out these three things. Do you find any similar thing? I mean, similar things. Yes, the first one and the last one are the same. You can just check out. 1, 2, 3, 4. 1, 2, 3, 4. Kind of. Right? So these two are same. So though we got three isomers, we can say that this actually leads to the formation of only two isomers. Hope this is clear. Now, let us take it this way. 1, 2, 4. So, oh. Now, this is unsymmetric. Now, let's see the available positions. So, to this, blocked, okay, blocked. And for this, blocked, okay, okay. For this, okay, okay, but here it is blocked. So anyway, all three positions are okay. Now, the second variety, and finally this. Check the three isomers. Check whether they are the same or distinct. They are distinct. You can even write the names, I mean the IUPAC names of these three products. You will find whether they are distinct or the same. So that is the best way to find whether they are the same or different. Now coming to the third variety. Taking 1, 3, and 5 positions. This is of course symmetric. Now when this is subjected to chlorination. See, for this, the two ortho and para position are very much open. When you consider this, both the ortho and the para are very much okay. And considering this, both the ortho and this para very much open, free, right? So again, it's all the three possible positions. I mean, all the three available positions. Yes. Now check out the three products. Check whether they are the same or distinct. Now, because we have started with something symmetric, obviously all three will be the same. Check them up. You will find that they are the same, right? That means just one isomer. So here the mantra is oh, no, AUS, adjacent, unsymmetric, symmetric. 231. So that is all about the fourth substitution. I mean, many more such groups can be taken for consideration, but this is all what I wanted to say. Now let us go for some other interesting reactions. A very important reaction, Birch reduction. Already seen this earlier also, but here it's going to be little different. In this, we have two different cases. What if there is a withdrawing group? What if there is a releasing group? Let's take these two cases. Now let us consider a withdrawing group. When this is subjected to Birch reduction, lithium or sodium in ammonia or of course alcohol. What is the product formed in this particular reaction? Let me give you the product straight away. Of course, we'll discuss the mechanism of how this particular product is formed. Look at this. Now, this is what we get when there is a withdrawing group. Let us see the mechanism, and then we'll again get back to this. Lithium atom loses electron to form Li plus. Of course, for convenience, I've taken 2. Now see this. Now let me just take a hydrogen out, and I'm now going to concentrate on what happens when See, this goes here. See, it actually goes there when electron comes and attacks this position. Let us see. You got an electron here, a negative charge, then this, of course, the NO2. Now the resonance. Bond goes towards this carbon. There's a negative charge at this carbon. Now consider an alcohol, say ethyl alcohol. Now this negative charge abstracts the proton and then the bond goes towards oxygen. So that is how ethoxide ion is removed. Okay. Yes. You got the hydrogen. Now on to the other hand, we have one more electron with us. Let us add that electron to this. Now even this also becomes a negative charge. Negative charge is nothing but two electrons. Right. Now again, take another molecule of ethyl alcohol. Abstraction of this hydrogen. Ethoxide goes out. That's it. That is the final product. So the thing that is to be observed in this is, when there is a withdrawing group for basic understanding, when you got a withdrawing group, observe this carbon. Earlier there was a pi bond, but now it's not there. This needs to be considered. So whenever there is a withdrawing group, simply speaking, the pi bond is withdrawn from that particular carbon. So this is how we can summarize this. Okay. Now the electron withdrawing group, as we know, generally withdraws electrons from the ortho and para position. In this case, we have considered the para one. So therefore, the electron generally at the ortho and para position. I have taken the para one. Okay. So that is very important. So let me actually tell you one or two interesting points here. Point number one. In case of electron withdrawing group, the pi bond at the carbon to which electron withdrawing group is attached is withdrawn. So simple thing is, when you have a withdrawing group, pi bond is withdrawn. That's it. And why the attack is at ortho and para positions in this case? Why is the electron attacking the ortho and para positions? See, the electron withdrawing group generally withdraws electrons from ortho and para positions. Therefore, the electron attacks electron, not the electrophile. The electron attacks at ortho and para positions. So this is about Birch reduction when you have a withdrawing group on benzene ring. Let's see what if there is a releasing group on benzene ring. A similar mechanism. Now methoxy group is of course plus M, it's electron releasing. In this case, when we use lithium or sodium in ammonia or alcohol, you can just imagine the product, I hope. Points to be noted. Meta has come into picture. The second one, the pi bond is not withdrawn, pi bond is retained. So when there is a releasing group, the pi bond is generally retained. Let's see the mechanism. For convenience, I mean to take meta, let me consider this particular resonance form of benzene. Yeah, as usual, lithium loses electrons to form Li plus. Okay. Then take the electron. As and when the electron attacks, at meta. Now here the attack is at meta because the releasing group releases electrons or donates electrons to ortho and para positions. So they are with maximum electron density. The one that has no electron density, electron deficiency is meta. So is the attack at meta. Come on. Now when the electron attacks this position, this one goes off. This, a hydrogen, this one, then this one. Now in the next step, this goes here, and this one goes to this carbon. Yes, a bond here, a hydrogen, electron, another bond here, a negative charge, then all these. Now the attack of electron, I mean the negative charge on hydrogen. I mean abstracts hydrogen in the form of H plus. So this goes off as ETO minus. Yes. Now we get a hydrogen there. We are still having this and an electron here, right? Now again, another electron comes into picture. This will now become a negative charge. A pair of electrons. Take the alcohol again. Abstract this hydrogen. We will get the final product. That's it. Now, the things to be noted in this particular case is point number one, see in case of electron releasing groups, the pi bond at the carbon to which the electron releasing group is attached is retained. So when there is a releasing group, pi bond is retained. Withdrawing group, pi bond is withdrawn. Releasing group, pi bond is retained. Yes. Now the next point is, see, the electron releasing group releases or donates electrons to ortho and para positions. Therefore, electron attacks the meta position. Meta position, which is, of course, electron deficient. Yes, because the electron releasing group is releasing electrons or is donating electrons to ortho and para. Therefore, electron attacks the meta position. Okay. Now, these are the two different cases in Birch reduction. Simply, the withdrawing group, whenever is present on benzene ring, the pi bond is withdrawn from the carbon to which the withdrawing group is attached. And when there is electron releasing group, the pi bond at the carbon to which the releasing group is attached is generally retained. Okay.